Okay, so let's get into the slides. So waves, we'll talk about transverse and longitudinal waves. We'll define wavelength, frequency, and the speed of a wave. We saw that waves carry energy. Power is the rate at which waves carry energy. We'll look at the differential equation governing the behavior of a wave. Okay. And we'll talk about how two or more waves combine with each other. And then we'll talk about standing waves, which is what you generate in a musical instrument. And then finally, resonance. Okay. So again, one more time, let me show you the simulation. Here is a string. This is an oscillator that is disturbing the medium. As the wave travels, the disturbance travels, as you saw. This oscillator, we said that the wave carries energy away. Okay. So since this is carrying energy, something must be pumping energy into the medium, and the oscillator is pumping energy into the medium. Okay. Soon as you stop the oscillator, soon as you stop pumping energy into the system, the wave dies. Okay. So you gotta, if you want the wave to continuously propagate, you gotta keep pumping energy into the medium. Okay. So this is the phenomenon that we are talking about. All right. Now, in this chapter, what we're talking about is mechanical waves, but a lot of what we say will apply to all kinds of waves. So mechanical waves are waves which need a media to travel to. A physical medium is being disturbed, and the disturbance propagates through the medium. Electromagnetic waves can travel through vacuum, and they consist of electric and magnetic fields, as the name suggests. And all these are different kinds of electromagnetic waves, light that your eyes are sensitive to, radio waves, X-rays, and so on. And then there's something called a matter wave. And this is something you'll learn when you get to quantum mechanics, I guess. So electrons and protons exhibit wave-like properties. Okay, so these are matter particles, and they exhibit wave-like properties. Okay, so, but I suggest that you go to this YouTube link and check out that video, which will talk about the matter waves. Okay. So here are some of the general features of a wave. Matter is not transferred, only the disturbance travels. So we saw that, we saw it in this simulation. See, the marked point is not going anywhere. It's the disturbance that's traveling. Okay. So, and all waves carry energy. Okay. So transverse waves, what are transverse waves? So this is a transverse wave. In this wave, the wave is traveling in this direction, and the particles of the medium are oscillating in a direction perpendicular to the direction of travel of the wave. So this is a transverse wave. Let me show you a longitudinal wave. Here is a longitudinal wave. So this is how this is a sound wave traveling in air. Okay. So to produce a sound wave, here is the oscillator pumping energy into the medium. And what a sound wave is see, so this is the diaphragm vibrating. And what it's creating is, see, high pressure regions and low pressure regions. So when it goes to the right, it creates a high pressure region, and when it goes to the left, it creates a low pressure region. And if you looked at the particles, each particle, see, the wave is traveling in this direction, and each particle is oscillating in a direction parallel to the direction of wave travel. So this is a longitudinal wave. This is a transverse wave. Particles are oscillating perpendicular to the wave travel. And in a longitudinal wave, particles are oscillating parallel to the wave travel. Now you have even more complicated wave. Well, waves. So in this waves, a water wave, you can go to the ocean or the lake. The wave is traveling in this direction, and a particle is going in a circle here. Okay. So this is in enough depth of water. Okay, so this wave is a combination of a longitudinal wave, of a transverse wave, and a longitudinal wave. So this is a combination of a transverse and a longitudinal wave. Okay, so transverse waves are waves where the particles in transverse wave elements of the disturbed medium move perpendicular to the direction of propagation. Okay. And you saw in longitudinal waves, the wave traveled in that direction and particles oscillate in a direction parallel to the wave travel. So water waves are a combination of both longitudinal and transverse waves. So let's define some parameters associated with the wave. This is the wavelength. So crest to crest distance or trough to trough distance is the wavelength. For instance, in light, in light, different colors have different wavelengths. So wavelength is associated with the color in light. The period T, denoted by T, is the time it takes for one complete oscillation for the particle, or it's the time it takes for one, if you stand here, the time it takes for one wavelength to pass you. Okay. And amplitude, like I said, is the maximum displacement from the equilibrium position. And the amplitude is related to the intensity, intensity meaning how much energy is being carried per second per unit area is related to the amplitude. So the period is the time for, if you're standing there, the time for one wave to pass you, or the time for one oscillation. Okay. Frequency and period are inversely related. Frequency is how many times the particle oscillates per second, or how many waves pass you in 1 second. If you're standing here, how many waves pass you 1 second per second. Okay. All right. When we mathematically describe the wave, it'll be convenient to define these two parameters. This is called the wave number, and it's 2 pi divided by lambda. So you can think of the number of waves in 2 pi, and omega is the angular frequency. 2 pi times the linear frequency is angular frequency. Right, so omega is also equal to 2 pi over t. And so these two parameters will be useful when we try and mathematically describe the wave. Okay, now is a good time to pause, and I will let you guys ask questions if you have any. Okay.